guess first things first. Is the audio okay, Natalie? Excellent. Thank you very much. Yeah, so never letting marketing people write a very long bio for me again, but thanks to them for that. Yeah, thank you all for coming out here. I appreciate it. I've worked as a radio engineer for about 10 or 12 years now, and like most of you, I've had to switch to doing more and more IT stuff, building out networks. And now specifically with Lawo, we're an IP media company. We build broadcast infrastructure. It's all IP based, so we do a lot of consulting with customers who are like, I'm about to build a radio station, or I'm about to build a TV station, or I'm about to spend a ton of money. Tell me what networking hardware to buy. And then we come in, we're like, here's how you can get rid of all of your money very quickly. That part I'm very good at. Everything else, we'll find out. So over the past couple years, I get a lot of exposure to different customers. We've seen a lot of different networks. And on the radio side, we're starting to get that like second generation of radio facilities where, radio facilities have started being built primarily as IP facilities about 10 years ago, 15 years ago if you were an early adopter. And now we're getting to that round where people are going, all right, let's do a refresh of the facility. We've had our stuff for about 10 years. It's time to go to round two. What's changed? What can we do better? On the TV side, TV is finally crossing the boundary from being like an early adopter technology for IP media, and now it's sort of the thing, if you're gonna go build a TV facility, you're probably gonna go IP at this point. We don't see that many people going, it's 2023, let me build an all new SDI facility. You can, but we won't help you with that. So yeah, the idea is to share, some of the things I've learned, and see if y'all got any questions, concerns. How many of y'all have worked with networking on a daily basis or build media networks? Great. Does anybody feel like shouting out any specific problems that really, really plague them? Users. Yeah. There's no fixing that one. You're cursed for all eternity. So I'm going to start with the things that I consider really, really important for you to know if you want to go build a media network. And the first thing is know what you need. Know what you want and know what you can afford, because those are often three very different things. We get a lot of people that come to us and they're like, I want to build a radio facility. I want it to be top of the line. I want it to be fully redundant. I never want to go off the air. We're like, great, that's what we do. Here's the quote for that. And then they come back and they say, what can I get for $20? And we go, not much. So there's a balancing act that you as an engineer have to do, right? And like, broadly speaking, that comes down to things like, okay, most of us want to stay on the air because that's how we make money. But you know what? If you're a music station and you're 90% of the time just playing automated tracks out of a playout system, you probably don't need to blow a ton of money into building some insanely resilient network when you can just spend $100 on an iPod off eBay and stick it out at your transmitter site, and that's usually enough to cover you. Don't waste money on things you don't need. Don't overcomplicate your life because you go and you look at some really cool network facility that somebody's done and go, wow, I want that. Yeah, so do I, but most people don't need that. So you have to be really, really careful there. Last thing with affording things, I'm not just talking about money. You need to understand what you know, what your skills are. If you're not a network engineer, don't go build yourself a really complicated network. It's gonna bite you in the ass, right? But maybe it is worth it, if you are a big facility, go hire some people that know networking. Go hire consultants to help you design it, right? Don't go beyond your means, because that ends up in a bad place and calls to us, and I don't want to answer the phone from anybody. So no problems, please. Before we sort of dive into the networking side of things, I want to just cover a couple of things that I'm going to talk about regularly. You're going to hear me say 2110 a lot. For those of you in TV, that's probably pretty familiar. That's the SMPTE set of standards for media over IP. If you work in radio, you've probably heard a lot about AES 67 or Ravenna or Livewire, things like that. The SMPTE 2110 standards, there are three of them that we care about: 2110-20, 2110-30, and 2110-40. Dash 20 is the standard for video over IP. Dash 30 is the standard for audio, and dash 40 is the standard for ancillary data. I'm a radio guy. I mostly care about dash 30. Dash 30 is basically a slightly stricter subset of the AES 67 standard. So anything that you get that says it's SMPTE 2110-30 compliant is going to be AES 67 compliant. And I would generally recommend, if you're going out and buying new IP equipment, just have it say dash 30 compliant. There's really no reason at this point that things are not dash 30 compliant. The big thing we care about with dash 30 is that it requires support for synchronous sending of audio. And what that means specifically is that all of your audio can be time aligned. So if you've got like multiple stage boxes for a band, and you've got two mics on a snare drum going to two different stage boxes, the audio coming out of those stage boxes onto the network is going to be time and phase aligned. So that's really important in a live situation, or when you've got stage boxes, multiple sources of I/O. It's less important in radio, where you just have a couple of microphones coming into the system, and after that you don't really care about phase alignment. But especially in TV, or if you're doing any live work, synchronous senders are important, which is why you want dash 30 standard. Any questions about that? Because we're going to go fast over a bunch of things. And if you got questions, you can shout them out. You can throw something at me. Hopefully you miss. That was your chance. Dash 7, 2022-7 is the SMPTE standard for what they call seamless protection switching. And what all this means is I'm going to take my packet of audio and I'm going to send it out twice over two different paths, right? So just send the same thing out two different places, and the receiver, whichever one of those arrives first, it's going to take the one that arrives first. And if one of those gets lost because somebody went and cut your fiber, it's fine. You've got another one. So dash 7 is the standard for media over IP networks, but there's also a lot of like proprietary implementations, especially with like codecs. So Gates Air has their SureStream, Tyline's got SmartStream, I think. You know, Comrex has their own everybody's got their own one, because when you're sending stuff over the WAN, it makes a lot of sense. Dash 7 can get very expensive. So it's something you want to be a little bit careful about. It's a really great technology because it gives you a really easy means of redundancy. Just build two damn networks. Keep them isolated from each other, and voila. You can make a change on your red network, your primary network, and blow it all up, and your blue network is still there and everything's great. But it gets really expensive because more often than not, the way we recommend doing that, the way you get the real benefit, is to build two completely separate, isolated networks. That's a lot of money to spend, and that goes back to know what you need and know what you want. Because most people don't necessarily need a dash 7 network, you know, especially on the studio side. Where dash 7 makes a lot of sense is in transmission, in your master control facilities, and the stuff that is super critical has to be on air at all times. That's where it makes sense to spend the money. Or if you are a network facility, you know, maybe your local or regional offices don't need it, but your head end, your master control, content capture, there it makes a ton of sense to spend the money. Questions? Great. The last one is SMPTE 2059. That's the SMPTE standard for PTP. PTP is Precision Time Protocol. This is, in an IP media world, you use PTP instead of black burst or word clock. This is how you get synchronization. If you don't have PTP in your media network, you don't have a media network. Nothing will work. You're going to have a terrible day. It's really, really important to spend a ton of money and time on PTP, because if you don't have it, you don't have a network. PTP is very important. Any questions about that? No, not at all. In fact, if you just go buy a Casio watch and you can use that, and you'll be very happy. Everybody else, though, it's very important for you. Excellent. Um, we see a lot of networks, as I said, we've seen customers build their first IP media networks, and for the most part, those all look roughly the same. For smaller facilities, they're either going to be a single switch, and everything just plugs into that, and you just have one isolated Ravenna switch and a couple of devices, and everything's great. That also applies to trucks, broadcast trucks, OB vans. Because of space limitations, they typically just buy one big chassis switch with line cards, put everything in there. It's a really good solution, especially if you combine it with something like Dash 7, where you just buy a big chassis switch with dual supervisors, you plug everything in, you don't really have to worry about any of the complexity that comes from having a ton of switches. It's easy, it works. It is a little bit limiting because you have one switch and everything has to be connected to that. So then you've got to spend a lot of money cabling everything there. So in radio facilities, for example, it doesn't always make a ton of sense. Typically what we see in radio facilities are sort of hub and spoke layer 2 networks, where you'll have a core switch and then you'll have a bunch of little access switches in all of your radio rooms. So you'll have some I/O devices in the rooms. Those connect to a little switch. That switch connects back to your core switch. This is a really common scenario. This is what most vendors will recommend, how you build your media network for radio. It works. It's a solid solution. It's relatively simple. It's easy to configure. People know it. There are a lot of pros in favor of this. And especially if you've got a smaller network or a smaller facility with not a ton of switches, it's a great solution. And it's something that we will recommend. But there are some limitations there. So the first is that you're kind of limited to a single core switch, right? So if that core switch goes down, then everything breaks. And your radio rooms don't function, your tech core doesn't function, you just sort of lose everything. That's not ideal for most people. Most of us get yelled at if we go off the air. So some of the solutions we see from customers is they'll have either 2 core switches and everything connected to both of them. That's an okay solution. The downside there is at layer 2, you tend to use IGMP to see all of the multicast groups on the network. With an IGMP layer 2 system, you have to have an IGMP querier that sends out messages saying, hey, what multicast groups are, what audio, what video is on the network, and who wants it. When you lose that querier, you have to have an election to say, okay, let's find the next querier, because there can only be one active querier at a time. That election process takes time, right? So depending on how you configure it, it can be 10 seconds, it can be 30 seconds, it can be 2 minutes, right? In some cases, that's acceptable because you will, for non-mission critical, for a music station, you can just fail over to an iPod at your transmitter site, wait for the network to sort itself out, and everything will be fine. You can come in later that day and sort it out. That's fine. If you're building a transmission facility or a master control for hundreds and hundreds of signals, 30, 60, 2 minutes of downtime is not acceptable. So what we see in those types of facilities are people doing stacked core switches. So stacking is a Cisco term. Other vendors call it like, I think Juniper calls it virtual chassis or things like that. There's a bunch of different terms. But the idea is you take a bunch of switches, take your core switches, link them together over a high bandwidth backplane link, and then one of those switches acts as the control plane. If it fails, the next switch takes over. So there's only one active control plane, and all the downstream switches see it as one single switch, which means you don't have to worry about an IGMP query or election, which is great. Stacking's a pretty solid solution in most cases. The downside is you are still limited to a single control plane. So there's still one single control plane, and if you come across a network bug, we've seen times where that crashes the control plane on the primary stack, and then it crashes it on the secondary stack a second later. So you lose a little bit of resiliency there. The other option we've seen people do with some of the higher-end Cisco, Arista, Juniper switches, you can do virtual VPCs is what Cisco calls it, MLAG, multi-chassis link aggregation groups, where you have two core switches in an active-active configuration. And that's pretty solid because typically you don't see one bug taking it out. You don't have to worry about a stack secondary coming online. That's a pretty solid solution, but you have to be careful with that because when you do an active-active solution like that, there tend to be limitations on things like how IGMP will work. So it's important if you do something like that to check with your switch manufacturer and say, here's what I'm doing. Is this going to be supported in a VPC or MLAG configuration? Because some things may not be. PTP as well is another one of those. So there are considerations there. The biggest issue we see with layer 2 networks is that once they start to get bigger, once you've got multiple core switches, once you've got lots and lots of leaf switches, you're essentially creating one giant broadcast domain, which means if an edge device connects in and starts broadcasting stuff, it goes everywhere. And it becomes very easy to have a broadcast storm that takes down your whole network. You're getting a lot of traffic on the network that a lot of your devices don't necessarily need to see and can even cause issues. There's a lot of devices on the market that if they see traffic they're not expecting, they just go, I don't feel like working today, I'm going to shut off. It's not ideal, but it is what it is. And you will see once you start working with dedicated IT networking engineers, they tend to frown upon making large layer 2 networks for exactly that reason, because it gives you a really large failure domain. You know, one device, on one switch can take out everything. And so that's really the core problem we find, is that you're creating a very large failure domain that's easy to trigger. Additionally, in layer 2 networks, you typically have to use spanning tree if you want to have multiple links so that you don't form a loop. Spanning tree works, mostly-ish. Most of us have probably been burned by spanning tree coalescence at one time or another. Spanning tree is not great, and additionally, it takes a lot of time to coalesce. Even with some of the rapid PVST things like that, when you do a spanning tree topology change, you can be looking at 10, 20, 30 seconds of downtime before your network comes back to functioning. And then you then have to go and wait on IGMP query elections and stuff like that. So you can be looking at easily a minute, 2 minutes of downtime. We don't love spanning tree. Try and avoid it. So for us, the solution is when it makes, wow, I had a whole slide about limitations in layer 2 networks. I wish I'd read the PowerPoint I wrote half an hour ago. Core switch, single point of failure. All traffic has to go to the querier. That's not efficient. IGMP query elections depend on spanning tree coalescence. That's not great. That single broadcast domain, really easy to have broadcast storms. Another two sort of deep tech things. IGMP v2, layer 2 networks, don't have support for source-specific multicast. What this means is that if you have two devices that are using the same multicast address, and you have a device, a receiver, that joins that group, there's no way for the receiver to say, I only want this audio from this sender. It's going to get it from both of those senders at once, which is going to result in just pure noise. So not having source-specific multicast allows devices to say, I want this multicast group from this sender. And that's a really powerful thing because it protects you against, oh no, I put in the wrong IP address, or I gave this the wrong channel number, and now I've got duplicate audio on the network and everything's falling apart and I'm crying. It's a bad day. Lastly, and this is a real fun one to troubleshoot if you ever run into it. There are, in a layer 2 system, IGMP snooping works based on the MAC address. So multicast IP addresses have a corresponding MAC address. However, because the guy who invented this system worked for a university, and his university was too cheap to buy a full block of MAC addresses for him, he had to create a mapping system. So for every multicast MAC address, there are 32 multicast IP addresses that share the same MAC address. And so, if you're in a situation where you are manually giving IPs to your multicast groups, you can inadvertently give two different streams, two different multicast addresses, but internally they use the same MAC address. So when a receiver subscribes to, let's say a speaker subscribes to audio from a microphone with a multicast address of 239.111, and you've also created a group of video feed, a 4K video feed with an address of 239.128.128.128. Those two are going to share the same MAC address, which means the switch is going to get your IGMP join. It's going to say, oh, it needs traffic to be being sent to this MAC address, and it's going to send you both streams. And all of a sudden, your little speaker is going to get your microphone audio, which is like 1.5 megabits of traffic, and it's going to get your 4K video stream, which is 12.5 gigabits. And all of a sudden, your network's going to collapse. And you're going to go and you're going to look in your network switch and you're going to go, what the hell is going on? And the switch is going to go, everything's fine. You've joined this multicast group. And it's not until you go start looking into the MFib tables and the MAC addresses that you start to see that, and you go, oh no. Now, the good news is, if you are using one of the proprietary implementations of AES67 like Livewire or Ravenna, this is all accounted for, right? So you don't have to worry about that. Where this comes into play is when you're doing multi-vendor multimedia over IP, and you've got to like manually IP things or do them according to a specific scheme. And if you don't take that into consideration, you can end up in that situation. And it is a nightmare to figure out. Been there, done that, would like to avoid it in the future. The way you get around these things is to build a layer 3 network. In a layer 3 network, you use multicast routing instead of multicast snooping. What this means a couple of things. One, you don't have a broadcast domain. Your broadcast domains become much, much smaller. So if you set up a routed network on a single switch, then the broadcast domain is confined to that switch. So now you no longer have traffic flooding all of the switches in your network. It's just staying within that one router. So things are much more contained. It also means that you're not dependent on a single core switch to be your IGMP querier, because each routed interface, so in a routed network, you configure an SVI or an IP address on a switch port, in which case it becomes a routed port. That then becomes your multicast router, which is responsible for sending out those IGMP queriers. And in the largest networks we build layer 3 routed to the edge, which means there are no switch ports in the system, which means that every device is connected in a /30 subnet, so there's only 4 addresses. And your broadcast domain is the switch and the device that's connected to it. And so if your core switch goes away, it doesn't matter, because all of your switches function independently of each other. So it lets you build a very resilient distributed network. It also lets you scale up your network to very large levels. So layer 3 spine leaf is the architecture we use. That's what the industry standard is in data centers, is to do spines, which sort of look like a core, and leafs, which are your access layer switches. The links between your leafs and your spine are these layer 3 routed links. And this solves a whole number of issues. One of the other things that comes with this is that you get to use source-specific multicast, so you don't have to worry about these duplicate multicast addresses causing you issues. The other huge advantage in a layer 3 routed network, it becomes incredibly easy to trace multicast flows. So it's very easy to say, I want to show me the mroute, so the command is usually called show IP mroute, for this multicast group. And you will see, okay, data is coming in to this multicast group from this IP address on these interfaces, and it's going out on these interfaces. So it becomes very easy to trace, okay, we've got a rogue multicast flow from this device coming in on this address. It shouldn't be there. That explains why we're having all these dropouts. It's a huge, huge troubleshooting tool. The downside of building a layer 3 network is that it gets a little bit more complicated. You've got to have more networking knowledge. You've got to build a you've got to have an underlying routing protocol like BGP, like OSPF, and you've got to have that additional networking knowledge. Your edge devices also have to have some level of support in order for you to get the full benefit. You know, the edge devices need to support IGMP v3 in order to do source-specific multicast joins. Not all devices do that. Additionally, if you are using a discovery protocol to advertise to see all your streams on your network like MDNS, MDNS by default uses a non-routable multicast address for its advertisements, which means that in a routed network, your advertisements don't go anywhere. So you have to either build in logic on the switches to act as an MDNS proxy and relay all these messages around, or you have to use an extension to the MDNS protocol to use it on a routable multicast address. So there's additional considerations you have to take in mind. Additionally, if you're using a protocol like MDNS for stream discovery, when you look at an MDNS advertisement, typically all that's in there is, hey, there's a stream here called Studio One Mic 1. If you're interested in it, connect to this device. And it will tell you information about this stream and it will give you the multicast address for that stream. The problem is, in order for that to work, you have to have unicast routing working. If you don't have unicast and multicast routing, then all of a sudden your stream connections don't happen. So you've then got to have logic on the edge devices to say, okay, we need to establish static network routes typically, where the devices have to have support for multiple routing tables. It adds more complexity. But when you are building a larger network, especially if you're doing video, especially if you're doing a network with a lot of switches that needs to be hyper resilient, it is worth it to put this effort in, because it saves you so many fundamental problems that exist within layer 2 networks. This goes back to know what you need, know what you want, know what you can afford, right? Not everybody needs this, but for the people that do, find the money, find the people to make it work. Next slide, we have a whole slide, just advice, and then we will be at an end because I've just been informed I have 5 minutes, so let's speed run this. This is a new thing. Know what you need, know what you want, know what you can afford. It's important. Get the basics right. If you don't have good power, if you don't have good HVAC, if you've got crap cables, it doesn't really matter how much you spend on boxes. It's all going to be trash. Get the basics right. Hire good people. There are 1,000,001 cool boxes in that hall. We will take all of your money and sell you all the cool boxes you want. I have never in my life seen a box that's worth more than a good engineer. Spend money on people, then come to us and we'll take your money. But for the love of God, hire good engineers. Spend on PTP, time and money. Think about it, because again, if you don't have PTP, you don't have a media network. None of your audio, none of your video works. All the devices are just going to go, well, good luck. Arista, Cisco, Meinberg, Evertz, all of these vendors that make PTP equipment, they've got excellent training videos about how to build resilient media networks. Talk with your vendor, right? Talk with us, talk with whoever you're buying a system from. What do you recommend? What are you willing to support? If you come to a vendor with some grand idea for some hyper-resilient network and they look at you and go, what is wrong with you? You are going to have a hard time getting support from them. So just keep that in mind. Know what your vendors can afford. Consider, if you're building a very important network, consider things like -7. Consider building a layer 3 network. Talk with your vendors, talk with network engineers, figure out if it makes sense for you. Lastly, this one's a little bit off topic, but when you start building larger networks, don't go configuring them by hand. Save the artisanal stuff for the flea market. When you build a network, use network configuration tools like Ansible, like Netbox, so that you can define what your network actually needs to look like and let them generate the code to actually build and configure the network. Spend time learning those tools like Ansible, like Python, like Netbox, because they save you so much time and effort, and they give you so much more power to build a resilient network. It's really, really worth it. Talk to us. Just talk to people. Ask for advice. We've all got stories to share. We've all got things we can learn. Just talk. Figure out what works. How are we doing on time? Can I quit? 3? Can I hand it over to questions? Excellent. Questions? Yep. Gotcha. So the question was, if somebody's got a layer 2 circuit over Ethernet for an STL to a transmitter site, how is this going to affect that? So layer 2 circuits for STLs and things are super convenient because you can simply just extend your audio over IP network out to your transmitter site, get access to all of your channels, everything's great. The downside is it can be dangerous because all of a sudden you've got a direct link, something goes wrong at your transmitter site, a flood happens, whatever, it can affect your main production network. When you have a routed network link, those broadcast storms can't traverse that link, which is very, very helpful. It also makes it easier from a network security perspective to do network segmentation, to put ACLs that say, hey, this is my link for my transmitter site. The only thing I'm going to allow across this link is UDP traffic on port 5004, which is RTP audio, and everything else is just going to get dropped. So it's certainly not the end of the world. We all do it, and that was how a lot of my STLs work, because a lot of vendors don't support layer 3. But I think it's worthwhile if you can make it work. MPLS circuits, if you want to use something like public internet, then obviously the quality of service gets really bad. So you need to start having 2 links, and you need to use something like -7, or you need to use like a codec with error correction, things like that. The one additional thing I want to point out is that when you start building larger networks, and especially when you start dealing with devices that use PTP, if you're just trunking audio across it, you can start to run into timing issues because the PTP isn't going to be compensated for across that link. The way you solve that is to have GPS clocks or PTP grandmasters at both sides. And that is our recommended workflow, is that if you're going to do multi-site distribution of audio, have GPS locked grandmasters at all sites so that everything is in time and in phase. There are some vendors out there that will offer to transmit PTP over WAN network links and their proprietary solutions, but they've had a good amount of success. Thank you. Next questions. We're out of time. That was it. You can find me floating around, or we are available at lawo.com. I'm happy to talk with anybody at any point. Thank you all very much.